Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 54. Now in the previous lecture, I was telling you that by studying the hydrogen atom lines, right? That is the lines obtained from hydrogen atoms present in outer space, right? The spectral lines that we get via combination of telescopes and spectrometers, right? We can understand and get to know a lot about the temperature of the source that is emitting the lines. As an example, I told you that starting from the n equal to 2, the population of the lines emitted from the n equals 2 level and the n equals 1 level for the sun, right? We can actually get the temperature of the sun by assuming local thermal equilibrium. And we can use the Boltzmann distribution, correct? Now, the key information here is that please note that the ratio, the number of molecules, the number of molecules present in the n equals 2 level and n equals 1 level, right, of hydrogen atom can actually be experimentally obtained. Okay, this can be experimentally obtained by comparing the intensities of the lines emanating from n equals 2 level and n equals 1 level. All right, so we can use the Boltzmann distribution as we've been discussing for quite some time now to get the temperature, right, by using this expression right here in page 3. Okay, are we good? In fact, the first 3 pages in this lecture are nothing but the last 3 pages from the last lecture. So for the sake of continuity, I have just left them as such. Please note this, okay? Yeah. So we now have to calculate T. We have to calculate T, right, from this expression. Given that we know the ratio of the number of molecules, right? Sorry, the ratio of the number of atoms, H atoms present in the n equal 2 level and n equals 1 level. That is given by this number. And we need to find out the degeneracies, that is G2 and G1, right? And we need to find out delta E, and we need to find out the temperature. Okay, this is our task. Okay, so I'm going to call this page 4, and we have to figure out G2, G1 and delta E, correct? Once we know G2, G1 and delta E, we can get the temperature, okay, right? Because we already know the Boltzmann constant. Now, to get G2 and G1, right? What is G2? It corresponds to the degeneracy of the hydrogen atom, right, in the n equals 2 level. And G1 is the degeneracy of the hydrogen atom in the n equals 1 level. We're going to use your class 11, 12 and first year chemistry knowledge, right? I'm sorry, it is not going to leave you, right? You have to use them. That degeneracy for any n, right, is given by Gi equals 2L plus 1, where L is what is the L? L is what is called as the azimuthal quantum number, right? So for n equals 2, right, my L equal to 0, that is the s orbital, right? That is the only possibility. Sorry, n equals 1, my L equals 0. That is the only possibility. Again, this is chemistry first year knowledge, so I'm not going much into explaining these, okay, right? Which implies my G1 is going to be 2 times 0 plus 1, which is 1. Similarly, for n equals 2, L equals 0, 1, right? In other words, I have the s orbital and the p orbitals, so the s orbital is going to be singly degenerate. That is, there is only one possibility. But what about the p orbital? That is the L equals 1. I have 3 possibilities, right? Px, py and pz. This implies that my G2 is going to be what? Is going to be 2 times, right? 2 times L plus 1. That is 2 times. Now, how many values of L are possible here, right? For there are going to be 3 p orbitals, right? 3 p orbitals, and there is going to be only one s orbital. So therefore, my G2 is going to be 4. I'll write it down properly. 4. Okay, right? So I'll write the summary here. So based on your class 11 and 12th and general chemistry knowledge, G1 is equal to 1 and G2 is equal to 4, right? How did we get G2 equal to 4? Because the n equals 2 level corresponds to both p and s orbitals. Now p orbital is threefold degenerate itself, so that's going to be 3 and this is going to be 1. And recall that we're not talking about any influence of any magnetic field or anything, so therefore we can assume that all the 3 p orbitals are degenerate. Okay, all right. So we have now obtained the G1 and G2. What about delta E? How do I get delta E? Any answers? Okay, so this is page 5. So to get delta E next, okay, so to get delta E, what do we need to do to get delta E? Now, recall once again from your class 11, 12th and then your first year knowledge, first year chemistry knowledge that whenever hydrogen atom undergoes a transition, right, based on both your Bohr's theory as well as what quantum chemistry subsequently tells you, it is that your delta E is given by negative RH times 1 by n1 square minus 1 by n2 square, right? Where my RH is nothing but the Rydberg's constant. What is its value? It's going to be given by 109,677 centimeter inverse, right? So you get the delta E in centimeter inverse first. So here what is N1? N1 is 1 and then N2 is going to be 2. So this is going to be 1 by 1 minus 1 by 4, right? Now therefore this is going to be given by what? This is going to be given, once you incorporate this number also, you can do the calculations to find out that this number is given by 82257.8 centimeter inverse. Okay, so but we don't have this delta E in terms of centimeter inverse. We need it in terms of joules, right? It's always better to use in joules because ultimately we are going to use it in this expression, right? Where the Boltzmann constant, it is better to use it in SI units as opposed to using it in a unit corresponding to centimeter inverse, etc. That will be more difficult. Okay, so how to convert this wave number into E equals hc over lambda, right? So this can be converted to joules, okay, right? By multiplying by the Planck constant and the velocity of sound, right? So E equals hc by lambda, delta E equals hc over lambda, okay? So what are we going to get now after doing that? You can do that as a homework. The number it turns out is going to be 1.634 into 10 to the power minus, it should be a very small number, I'll just confirm. Yeah, it's minus 18 joules. Okay, so this is the magnitude of delta E, which is my E2 minus E1. All right. So where do I get this formula from? Well, this formula is obtained from the Bohr's theory as well as from introductory quantum chemistry. I'm not going to derive this because I expect the audience to know this. All right. Yeah. So as a homework, you can just look up as to how exactly this formula came up. And another homework would be to convert the centimeter inverse to joules here. Okay. So from this page, I will just retain the degeneracies and I'll delete everything else. Now all that is left to be done is to just use this expression right here, right? Use the Boltzmann distribution to get that. My 5.15 into 10 to the power minus 9 is equal to 4 times e to the power minus delta E, that is minus 1.634 into 10 to the power minus 18 divided by T times the Boltzmann constant. The Boltzmann constant is roughly 1.38 into 10 to the power minus 23. Now, the only variable in this equation This is 4 times, I'll write it like this. Right? So 5.15 into 10 to the power minus 9, sorry, yeah, not 19, minus 9. Okay, right? So everything is an exponent. So this is 4 times e to the power something. Well, this is the delta E, and this is the Boltzmann constant, and this is the temperature. So we need to find the temperature. I'll leave it to you as a homework, right? To evaluate the temperature. But what should you expect? Hey, we've had like close to 50 lectures of astrochemistry. What is approximately the temperature of sun that you should be getting? The answer you should be getting should be close to 6000 Kelvin, right? So this should be around 5780 Kelvin. All right. So what is the bottom line? The bottom line is that from the Balmer line, right? From the Balmer line, right? And by knowing the intensities of the various lines emitted from the hydrogen atom, we can get the information about the temperature of the interstellar medium, right? The source that is emitting. And of course, you would expect it to be hot because there is substantive amount of light emitted from n equals 2, even though it is not the ratio of the number of molecules, number of hydrogen atoms in n equals 2 level to n equals 1 level is 10 to the power minus 9. That is sufficient enough for temperature to be approximately 6000 Kelvin. Now you can imagine that in the stars which are much hotter, right? You can imagine the temperature therefore would be much higher than this. Okay, so this is the significance of the Balmer line. This is one significance from out of many, right? Of the Balmer line series, right? Which corresponds to all the line series starting from n equals 2 to astrophysics and astrochemistry. Okay, that we can find out the temperature. Now, the next point I want to address is the idea of ionization. Now, see, next point. Ionization from the hydrogen atom spectra. Now, we all know that you may be asking me a natural question. It is that, okay, see, we are talking about such high temperatures, 6000 Kelvin, etc. How do you still expect the hydrogen to be in atomic form, in neutral atomic form? Won't it be, getting ionized into its charged atomic form? That is like, won't it become H plus? Won't ionization happen? And if ionization does happen, how do we know that ionization is indeed happening? Well, the answer is that, see, we discussed about the various the wavelengths at which the Balmer line happens, right? So the Balmer line, right, starts off from your H alpha, which is around, say, 656 nanometers. Okay, right? Now, starting from 656 nanometers, right? There's a range. Okay, right? Now, what is the H beta? The H beta is going to be, I told you that the H beta is going to be like around, if I'm correct, 486 nanometers. Okay. Now, H gamma is also important. H gamma is going to be, let's say, around 431 nanometers. Yeah, 431 nanometers. Now, see, the point is, if you look at the difference between H alpha and H beta, right, the difference is like 656 minus 486. But between H beta and H gamma, that is 486 minus 431. The difference is getting narrower and narrower, right? Now, at some stage, in any series of the hydrogen atom, in any series of the H atom lines, right? What happens is that, you start off with a significant difference between H alpha and H beta. The line difference, it is entirely dependent on the delta E, which can be seen from this formula. Okay, right? So the difference between like H alpha and H beta is, we're talking about like close to 180 nanometers, right? But it's only 50 nanometers. So let's say, you progressively, like keep going between any two lines. At some stage, the lines, right, are no longer discrete. In other words, let's say, if this is like decreasing the wavelength, right? You have one line here, you have one line here. I mean, you obtain you have one line here, you have one line here, you have one line here, you have one line here. Let me just draw them with equal intensity just for educational purposes. And then you have one line here, you have one line here, and you have, you can no longer differentiate between, the lines. These are all discrete lines. And suddenly over here, right, you get a continuous range. What does it tell you? What it tells you is that until now, right, until this stage, hydrogen atom was a bound system. And it was unionized. But the moment you go to the continuous regime, recall I think a few tutorials earlier, right, I had told you that you don't always get discrete lines alone, as part of spectral lines. It has to be a bound system. Once ionization happens, your hydrogen atom gets ionized, and you get what is called as a continuous series of lines. Okay, right? So that is how you know that ionization has actually happened, right? So what do I say when I say ionization has happened? I'm talking about this reaction, H gas becoming H plus gas plus an electron. Okay, right? So because at very higher temperature, right, ionization happens, and so therefore you see a series of continuous lines in the spectrum. Now for the Balmer series itself, right, you start off with the H alpha line that is 656 nanometers, right, and all the way this continuum appears around 365 nanometers. Okay, right? So starting from 656 nanometers, this continuum appears at 365 nanometers. So you understand that at this particular wavelength, ionization happens. Okay, right? This is for the Balmer series. For starting from n equals 2. Okay, right? So now you understand that ionization happens, right? Before I proceed further to the next topic, I'll tell you one quick point about what I'm not saying. I avoid discussing about the other lines starting from n equals 1, n equals 3, blah blah blah, etc. Okay, right? I avoid about these lines because you've already seen a lot of these lines in your class 11, 12th. Okay, this is because I avoid discussing about the lines because because these lines do not provide us much new astrochemical insight. Of course, those lines are also going to be seen in the hydrogen atom spectrum, right? And in our particular context, in this class, okay, right? Of course, if you work on astronomy and astrophysics and astrochemistry as a research topic, maybe at that level there could be some astrochemical insight. But at our level in this class, we're not going to be getting too much of new information by studying the other lines also. That's why I limit my discussion to the Balmer series alone. Okay, please note this. All right. So now, while we're on the topic of ionization, okay, right? The topic of ionization leads us to a very interesting topic, okay, right? A very interesting topic called as leads us a very interesting, a powerful, and in fact a game-changing equation, right? To a game-changing in astronomy and astrophysics. I mean, by extension also to astrochemistry. It is what is called as, can you guess the name of the equation? Right? We're talking about hydrogen atom ionization, especially in the context of local thermal equilibrium. The equation is what is called as the Saha equation. Now, this was proposed by Professor Meghnad Saha, right? Who was an outstanding astrophysicist and astrochemist from India. Okay, so I'll explain what the equation is, okay, right now, and how it actually led to, a game-changing understanding of the composition of stars, etc. Okay, so the Saha equation is given by, I'm just going to call it as like SE. So your Saha equation is actually given by, for any species, okay, say some monoatomic gas, right, such as for example hydrogen or any gas, right, is undergoing ionization, undergoes ionization in space. The Saha equation is given as, this is for some species, A giving A plus plus E. Let's, to begin with, consider only monoionization. That is, you can also, subsequently undergo this reaction of A plus giving A double plus, etc. But let's limit our discussion to just A giving A plus plus E. Okay, right? Let me call this a species 1 and a species 2. Now, the Saha equation, one variation of this is given by N2 by N1, right? I'll explain the terms very soon. Okay, is given by, right? So this is what is called as the Saha equation. Don't worry, I'm not going to derive this equation. It can be readily derived from the statistical thermodynamics we saw in the previous lecture, but there is no need for us to derive this in this lecture. I'll just explain this to you and I'll tell you the implications of this equation. Okay. Now in this equation, my N2 is nothing but the number density. Your N2, N1 and Ne are the number densities of, like, by E I'm talking about the electron. So this is Ne, this is N2 and this is N1. Okay, so these are the number densities, and my T is temperature. H bar is, h by 2 pi, that you should be knowing from this class. Me is mass of the electron. Z2, Z1 are nothing but the partition functions of A plus and E, are the partition so Z2 and Z1 are the partition functions, and what else? Kb is the Boltzmann constant. And this term E, right? E is the ionization energy. Okay, right? So this is one version of the Saha equation. Of course, you can make further approximations also, right? So, I mean, before I explain further, note an important point. I will not derive this. Okay, I will not derive this in the class, but I'll tell you that it can be very readily obtained from the same Boltzmann distribution, and then by using the idea of what is called as the translational partition function for electrons. Okay, right? But it's easy. But then it will be time consuming and I have to teach some more parts in this course, so I'll just avoid deriving this. Okay, so now that we have the Saha equation, what does it tell you is that it connects, okay, right? It connects the number densities of the species getting ionized, right, with the temperature and the number of the densities of electrons also, right? So what it does is, what the Saha equation does is, your Saha equation connects the number densities, number densities of the species undergoing ionization, right, including the electron, with the temperature of let's say the source in space. Okay, right? Now, what is its implication? This is the meaning of this equation. Okay, right? And you can of course make various assumptions about the partition functions, and you can compute the temperature, right? And once you have an idea about the number densities, okay, and the number densities can also be obtained from the intensities, right? So this is the meaning of this equation, right? The Saha equation. Now, what is the implication of this equation is fascinating actually. Now recall that I had in this course, say around probably in lecture 30ish or something, 20ish, 30ish, maybe 40ish also, I forget when, we were talking about detecting atoms for the first time in outer space, right? Using the Fraunhofer lines and all that. Now, that led us to the understanding that whatever is present on Earth, right? The same stuff, that is like the same elements are present in Sun also, for example, correct? Now, this actually led to a faulty conclusion. Okay, this observation led to the faulty conclusion that whatever element is present on Earth, right? The composition of Earth is the same as the composition present in Sun also, for example. Okay, right? Now, this equation was propounded around, approximately, let's say 1920. Okay, right? So the implication of Saha equation, implication, and I would say consequence. So until about 1920s, a misunderstanding was that the composition of stars was the same as that of Earth. See, this is a beautiful point, right? It tells you that even though the stars composed of the same elements, it gave you that valid conclusion. But nonetheless, what people came to the wrong conclusion was that just because the same elements are present, the compositions are also the same, right? But that was obviously wrong. Okay, right? What the Saha equation enabled was that what SE enabled, and how did it enable? By computing the various number densities. Okay, by computing the various number densities, by computing number densities, right? It enabled that the compositions of the stars are very different. Star very different. I mean, it can be laborious. I mean, it can be a laborious exercise for us to compute the partition functions and then compute all the terms here. But it can be done readily. When I say laborious, it's laborious in terms of time. So we are avoiding the exact computation. That can be done in a course exclusive to astrophysics or astronomy. But I'm just going to take the conclusion. Okay, the conclusion is that by using this equation, just because the elements present in the Sun and or any star is the same as the elements present on Earth, it doesn't tell you that the compositions are the same. Okay, so by applying Saha's equation, this was predominantly done by Professor Payne from Harvard University. Okay, right? That the star compositions are very different and they are predominantly dominant with hydrogen and helium. I'll tell you what I've written here. I've written in the bottom part of the board. So the star composition is very different from what is known as from what is found on Earth, right? And they're dominant. That is, the star composition is dominant with hydrogen and helium only, predominantly. All right. So this was a very vital conclusion that was obtained by applying this equation. How exactly they apply the equation, we did not see in this course, but it can be done as an exercise if you look up online, or you can take it up in any astronomy or astrophysics course. Okay. On that note, I end this lecture, and we shall look up about more aspects of spectroscopy in the next lecture, that is. Thank you so much.